Hello, so I will be talking about the sound static data race verification for C. So I will also start with a definition of data races. So our definition that we use is that there is a data race between two accesses A and B if the following condition holds. So the accesses are done to the same memory location. The accesses are done by different threads. At least one of the accesses is a write. At least one of the accesses is non-atomic. And there is no happens before relation between those accesses, so there's no synchronization. What is our dream is to have sound and static automated software verification of data race freedom. And what does this mean is that we want to verify data race freedom. We want to do this using sound static analysis tools. We want to verify the data race freedom in real-world programs. And we want to do it automatically. So meaning with a push of a button, we want to reanalyze the program when it evolves. So after we have done the dynamic analysis and found all the bugs, fixed the bugs, we want to make sure that there are none left. So sound static data race freedom verification is a long-standing challenge for more than 20 years, but okay, I don't, So, but the focus has traditionally been on log-based synchronization. So the current tools handle log-based synchronization rather well. So such examples as this function foo on the slide, where this data field is accessed, but the access is protected by the mutex, and if this is run by different threads, then everything is fine. But unfortunately, there's a big gap between the current benchmarks and the real-world programs. So what we have for current benchmark, the status quo benchmarks are the International Competition and Software Verification benchmark set. And this includes some 700 verification tasks, out of which only 2% are tasks where there is no tool that can handle them. So it can seem like everything is solved, but this is not the case. And why this has happened is because normally, as this benchmark set is compiled by community effort, all the benchmarks that get contributed are the ones from the evaluation packages, from the methods that they have done. So to bridge this gap, we asked our first research question: what are some concrete multi-threaded implementation idioms that prevent the existing verifiers from verifying data race freedom in real-world programs? So for this, we needed real-world programs, and we needed the verification tools, and then we ran them on them, and then we extracted the parts where these tools failed. So there are other works in the literature that we saw that run dynamic tools on real-world C programs and Java programs, as well as bugs have been extracted, the data race bugs from Golang language, but as far as we know, those idioms that are correct have not been extracted yet. So I will present the idioms first. So this is our main contribution. So let's focus on the right things to solve from now on so that we don't get distracted. So to ensure data race freedom in a program, the accesses must be separated either in space or in time. So on these idiom slides, I have three different ways how I say the same thing. So there's a textual representation, there's the idiom, the code, and then there's some visual representation on this time and space axis that shows the semantics of those idioms. So in this first example, so for space separated accesses, there are many ways how data is passed to the threads that ensure space separation. So in this example, syntactically, within the for loop, a fresh struct is created, and then this fresh struct is given to the worker thread. So each of the worker threads access their own fresh struct, so that ensures the separation in space. Another example of this data being passed to threads is now that the main thread creates an array, and then within a for loop passes an indexed address from this array to each thread. So each thread has their own part in this array that they access. So here we have this space separation. But in this example, there's also time separation involved, because on the line 4 here, the main thread actually writes to this array first. So there's a happens before relationship here. So before the main thread passes the ownership for this location in the array, it writes, and then the threads are able to write into this position. So this time and space can be intertwined there, and this makes proving these things even more difficult. So space separation can also be ensured using thread local storage. So there's this thread specifier given by GCC that ensures that each of the threads have their own copy that they can modify, and this is ensured by construction. And then there's another specifier from the pthread library called pthread_key, which can only store pointers, so there's an additional indirection here, but this is also ensured by construction, so each thread has their own copy that they can write to. So moving on to time-separated accesses, there are thread joining idioms. So here, syntactically, what happens is threads are created within a looping construct, and then the same threads are joined within the looping construct. So all of the accesses that the main thread does after the threads are joined are in a happens before relationship. So there's time separation. But the threads themselves, when they do accesses, there must be some synchronizations, either it's locks or whatever. And then a variation of this is also, instead of joining the threads, there was a shared global integer where the main thread was counting how many threads are still alive. And then if that reached 0, then there's a happens before relationship again between the main thread and the worker threads. And there were also some other idioms that we saw for that ensured time separation. So these were based on value-based synchronization. So here, what happens is on line 18, main thread writes to a global variable. And then after this write, using synchronization, sets the ready flag to true. And then the worker threads will wait until the ready flag becomes true, and only then continue to read from this global variable. And in practice, this busy looping would be replaced by conditional variables. So now that we have seen some of those idioms that we are not able to handle yet while trying to prove database freedom in C, there are more examples in the paper, but I will go briefly through the methodology that we used. So first of all, the data collection part. So for the real-world programs, we were fortunate to find an existing collection of real-world C programs that was compiled by Hong and Ryu, but we unfortunately had to exclude some of the programs for evaluation, so we were left with 18 programs, and the exclusion was because some of them were single-threaded, so there was no point in running the tools on them, and with the current static analysis tools, we cannot really handle projects where there are massive amounts of external code, so these wouldn't give meaningful results for us. So for the tools, we used tools that participate in the international competition on software verification SVCOMP from the no data race category. And these tools use various methods for trying to prove database freedom in C. So there's abstract interpretation-based tools, model checking tools, and also satisfiability modulatory tools. And we acknowledge that these tools were not meant to be run on real-world programs. So this is quite depressing, but a lot of the results here, what you can see, are just blocked by engineering efforts. So, but we weren't really interested in this, what are the engineering efforts we want to do to get somewhere. So we actually, for this, we had to extract the idioms to see where they actually fail. We extracted those idioms, and then we asked our second research question: how well do existing verifiers handle each of those idioms when extracted into isolated microkernels? We did this because we wanted to validate that indeed these idioms that we extracted, the current methods cannot handle. So here are the results. So this table is a bit different than the table we saw before. Because for these micro examples, we know the ground truth. So we know that some small examples are indeed data race free, and then we also created RACI variations of those programs. So here, unsound means that a verification tool, even if it proved the correct program correct, it also claimed the incorrect program to be correct, which we don't want because we want soundness. So there are a few, other than the unsound tools, there are a few ones that we can solve, but mostly we're not there yet. And for the third research question, we asked how prevalent are these challenging implementation idioms in real-world programs, because for the extraction part, we had to exclude some of the programs from the original set, but we actually wanted to include a larger set. So what we did, we took the syntactic markers of these idioms and we counted them in the whole benchmark set, including also the ones that we excluded for the actual tool evaluation. So here's the results for the prevalence. So for the subset on which we ran the tools, these are pretty okay, prevalent. Then for the whole concrete suit, what we are interested in here is that there is at least one or more of those syntactic markers also present in those programs that we excluded in our initial evaluation. And that is the case, which is nice. And also by the percentages, they are present in many of the benchmarks. And one thing that we also wanted to validate was that indeed in SVCOMP that we don't have these idioms yet. So in the SVCOMP benchmark set, we have a really good coverage of those locked-based synchronization tasks, but for some of those syntactic markers, there was 0 tasks that included them. So now we have contributed the extracted set also to the SVCOMP, and we hope that the tools will start to work on these problems and soon solve them. So to conclude, lock-based idioms are pretty well supported by current race detection tools, so we can prove data race freedom in programs that use lock-based synchronization. However, real-world C programs actually rely on non-lock-based idioms as well, and these idioms are poorly supported, and we should try to figure out new methods to support these idioms to get closer to verifying actual real-world code using static analysis tools. That's all. Thank you.
Thank you for a great talk. Any questions, comments? Okay, let me start. So you used the benchmark from the concrete work, and how concrete work for these benchmarks? I mean, did you evaluate concrete on the same research questions?
No, because I think they actually work on Rust, right? So
they somehow translate from C to Rust and verify the data race freedom there. So it kind of proves the absence of data races in C.
Yes, we didn't independently evaluate them because we were really interested on, we want to go forward with having static analysis tools for C. So we want to still analyze C and do it on the C source without this translation. So that's our goal.
Okay. Yep. Any further questions? Yep.
Hi, this is Saan from NYU. Thank you for the great talk. It gave me a really good idea of kind of the landscape today. I'm curious about benign data races as well, where that's kind of, I feel like that's something we haven't even started to look at. Do you see, across the different benchmark sets and kind of example code bases that you've looked at or examined, do you see any cases of benign data races that are either going undetected, which is, I guess, in some sense, good that benign data races are not are not recognized as errors, or do you see that benign data races are also kind of grouped into this set of potentially harmful behaviors?
Mm-hmm. So in our work, we consider all kinds of. So we also consider benign data races, but yes, I have seen a lot of for example, logging messages. If your log messages raise a bit, in the real world, we wouldn't care, but in this formal world, we do care. So we want to find them all and prove data race freedom for even benign data races.
One more question.
Could you elaborate a bit on this benign data race thing? I'm a little lost because I thought whenever there is a data race, it's always sort of like a violation of the compiler's guarantee or something. Namely, your code may be completely unpredictable. I think there was kind of a very good talk paper or something showing that in the world of C, there's no such thing called benign race, because you do not know what your compiler will do to your code whenever there is a race, right? Can you elaborate on that a little bit?
So for us, yes. So for abstract interpretation based on the work that we do, we consider benign data races and we want to be all correct. But the thing is, people have been moving away from soundness because the sound tools are not there yet to be applied on large-scale real-world programs. And then the first thing that gets left out are those benign races, because if you don't have a safety-critical system, you don't really care, because nobody, it's just a mindset that in the real world.
Yeah, I'm just a little bit confused by what is even a benign race. If I have a race, I don't know how the compiler is going to compile my program. Then how can I know whatever is benign or malicious? That's my confusion. But maybe we can talk off.
Yes, sure.
Yeah, let's thank the speaker again.